Okay, so this week we are talking about climate models. So our goals here are first to understand what climate models can and can't tell us about our climate, and then for you to be able to use some basic climate models to examine how our climate system works. So first, let's talk what is a model. And I like to start with this quote from statistician George E.P. Box. He said, "All models are wrong, but some are useful." All models are wrong, but some are useful. So a model is a mathematical representation of the processes making up some sort of system. So in this context, we're interested in climate models, so mathematical representation of the climate system. And so any model is going to be a simplification of what's going on. Right? The model is going to be much less complex than the real world system that it is representing. So that's why all models are wrong. No model exactly matches the thing that it is a representation of. However, models can be useful. They can capture important elements of the processes that make up that system and allow us to understand the dynamics of that system to make projections about the effects of different choices that we might make. So every model is going to simplify the world, but it's going to do that in a way that is helpful to us in engaging with the world in making decisions. And it is that simplification that makes models able to be useful. If a model was as complex as the thing it represents, then the model wouldn't really be useful to us. We wouldn't be able to get a grasp on what that model is doing. So for the climate system, we've got a little diagram there to the side of what goes into creating and using a model. So there's two sides that we are bringing in observations of the actual world into developing our model. So one set of observations helps us to define the basic physical, chemical, biological properties of our world. So we want to understand these general laws of how the different things that make up our world work. And then we also use those observations to set the parameters for the model. So what are we starting from in our use of this model? So that gives us the principles that the model is going to work on. Then we feed in observations about the state of the world. So these are things like our radiative forcings. What is the actual amount of CO2 in the atmosphere for each year that we're going to run our model on? So we combine that with these basic uh, basic processes that we've documented, and that gives us our model results. Right? The model takes these observations about the state of the world, calculates what changes are going to occur based on these more general laws of nature that we've got, and it spits out some results. Says, here's what is going to happen according to the model. It simulates the future for us. Then those results we can test. As we get observations of what actually is happening, we can compare those observations to the results of the model, and we'll see if the model is getting it right. And if the model is getting it right, then we become more confident in using additional projections by that model to, get an idea of what our future holds in store for us. And if the model's not quite getting it right, then we can circle back and try to figure out, well, where is it going wrong? What aspect of that model is going astray from how the world really works? We can adjust that, see if our adjusted model does a better job. So as we're building these models, there are a number of features that we would have to take into consideration. And we can describe models in terms of which features they have, and we can distinguish different types of models based on the sorts of features they have. And some of the main features that we might look at in a climate model would be, first, the spatial scale and resolution. So how much of the Earth is this model modeling, and how detailed is that modeling? How much fine scale detail can this model show us over that area that it's covering? Then we also have temporal scale and resolution. So what's the time frame that this model is running over, right? Is this a model that is predicting, the weather tomorrow? Is this a model that's going to predict climate 200 years from now? Right? How long of a time period are we covering? And then temporal resolution is how much detail do we get in there? Are we getting hourly forecasts? Is it daily? Are we looking at month to month kind of changes? And then the set of variables and parameters that the model takes into consideration, because there are so many different interlocking systems that affect our Earth's climate. And so some models might try to model all of those processes and incorporate them all within the model. Other models might set some of those things aside and say we're only looking at a certain number of these processes, and then anything that we're not modeling within the model, we're going to feed in as external information. So if we're looking at climate models, there are kind of three tiers of climate models based on the complexity of the model and the amount of detail that it's able to give us. So the least complex climate models we have are what are called energy balance models. And this is basically a calculation of the relationship between energy coming into the Earth system and energy going out of the Earth system. So if you think back to that Stefan Boltzmann equation that we looked at several weeks ago, right? The one that predicts that the Earth should be about minus 18 degrees Celsius. That is a extremely simple energy balance model. That's about the simplest energy balance model that we can have. And of course, we already saw why that model is probably too simple for our purposes. We need to add some additional processes into that model to get a good sense of what's really happening with the Earth system. So, we can add some equations to that and get a little more complex energy balance models. But eventually, if we keep adding stuff to that model, more and more elements of how the Earth works that we try to incorporate into our model, then we go up the scale to working with what are called Earth models of intermediate complexity. I think that name should be pretty self-explanatory, right? It's the middle set of models, and these are notable for incorporating space and time elements to them. So our Stefan Boltzmann equation, that's just a single equation. It's just giving parameters for the entire Earth as if the Earth is just like a single point, and a single data point that's looked at in that model. If we start to differentiate what's happening in different parts of the Earth, right? There are going to be different climate processes and different effects happening in polar areas versus the tropical areas, etc. We start differentiating things by space, and if we start looking at how things will develop over time, so not just the final balance that's achieved, which you get by solving out a single equation, but we look at how we're going to develop over time, then we're getting into Earth models of intermediate complexity. And then the most complex models that we have are what are called general circulation models. And the diagram here on the screen is an illustration of kind of what's going on within a general circulation model. And these are the models that are used for a lot of the projections of future climate change that you may see in the media, that you may see in the Intergovernmental Panel on Climate Change reports, which we'll talk about in more detail next week, who the IPCC is. A lot of these projections are made with these general circulation models because they're the most complex. They incorporate the most different processes that are going on in our Earth. The trade-off to that is that they require an enormous amount of computer resources to run. You're not going to run a high-level GCM on your laptop with just your laptop memory and processing power. So what you see in the diagram there, we've got our Earth broken up into all these little blocks. We're looking at multiple layers of the atmosphere, and it's differentiated over the surface of the Earth. We've got the ocean incorporated, so we're looking at how heat and CO2 are exchanged up and down the water column within the ocean. We've got soil and vegetation as distinct layers, so we're going to look at the element of the carbon cycle, where carbon goes back and forth between the atmosphere and the biosphere. You see the ice sheets are incorporated into these models. So we're looking at the dynamics of how ice sheets grow and shrink and how that may affect things like the water that's in the ocean and the albedo of the Earth. We're looking at processes of formation of clouds in these models. So they can track where clouds are going to form, where moisture is moving through the atmosphere that can produce precipitation. All of those different processes get incorporated into these GCMs, and that's why they're so complex, why they take so much computer power to run. So here I want to dig in just a little bit more to that idea of spatial resolution. So spatial resolution, again, is how much detail in terms of where stuff is happening that our model gives us. And as we've advanced in our amount of computer processing power that we have access to and the detail of our understanding of the Earth system, we've been able to increase the spatial resolution of our GCMs. So what you're seeing here is an illustration of the spatial resolution in the GCMs that were used in the first 4 reports put out by the Intergovernmental Panel on Climate Change. So the first assessment report had sections of the Earth that were 500 kilometers to a side. And so what you're seeing here is, Europe and the North Atlantic. It's kind of hard to even recognize it in that first one because those chunks are so big. And we call those chunks voxels. So they're volume pixels, essentially, right? Because they're these little rectangular boxes that cover sort of a square of the Earth to a certain amount of depth in the atmosphere or going down into the ocean that these voxels cover. And each one of them has a single value for each variable that we're incorporating into our model. So there is a single temperature variable for each voxel. There's a single, for the atmospheric ones, there's a single moisture, humidity variable, etc. So then you'll see they cut that in half, the size of the sides of those voxels in half for the second assessment report. So now there's only 250 kilometers to a side. When you do that, you cut the size of a side of a voxel in half, you get 8 times as many voxels, right? You've got twice as many going east to west, twice as many going north to south, twice as many going up and down. 2 times 2 times 2 gives you 8. So that's a lot more of these voxels, and so that means it needs 8 times as much computer power to run this model. So it's going to take 8 times as much processing from your computers to do that. And then you can see they continued to make the resolution even more finer grained. Third report got it down to 180 kilometers to a side. Fourth assessment report got it down to 110. And so by that last one, if you're familiar with the map of Europe, you should be able to see pretty clearly everything that's going on there. We've got very fine-grained information about our climate system in that last one. But again, the trade-off is that it just takes a lot longer, a lot more energy from our computers to run it. And so at a certain point, the gains of detail that you might get from increasing your spatial resolution are just not worth it in terms of the resources that it would take to run that model. Okay, so we've got a model. We can input some data into it. It can spit out a projection of what's going to happen. How do we know that our model is telling us anything that is relevant to what's actually going on in the world? Well, the main way that we test these models is through something called Hindcasting. So with Hindcasting, we give our model data from some point in the past, and then we use it to predict the present. And if we can forecast the present accurately using data from the past, then that gives us some confidence that we can forecast further into the future and it will remain accurate. So what you're seeing there, that graph is showing the relationship between a certain set of GCMs and actual climate data since the very end of the 1800s, right? That's our period over which we have high quality surface temperature observations, as we were talking about last week. That is the black line. So the black line is the actual temperature data that we have. Then all of the really skinny little orange lines are individual model runs. So these models all have a probabilistic element. Right? There's an element of chance or randomness in them because that's how our climate system works. There's an element of chance or randomness to those natural processes. So what we do is rather than just running the model once and just taking that result as like the result, we run the model many, many, many times, hundreds of times that we'll run these models. And then we average all those results together so that all the little ups and downs that we get kind of smoothed out. And so what you're seeing there is all of those model runs that are in the orange, when they get averaged together, that gives us the thick red line that runs kind of down the middle of that. The thick red line is the average from all of those different model runs. And what you can see there is that our models did a pretty good job. The overall shape of the ups and downs of our global temperature was pretty well predicted by this Hindcasting model. Starting off the model with data from the 1890s, it was able to figure out where we'd be in the 2000s. Didn't get everything exactly right. There are some ups and downs to the actual temperature data that weren't quite captured in the model run. So you'll notice there's that big spike towards the end. That was 1998. We had this really strong El Nino phenomenon made the Earth for that year really unusually warm. Looks like our model wasn't able to capture that dynamic. That's kind of a known thing. El Nino is tough to model and predict. So models didn't quite catch that kind of 1 year's spike, but the overall trend, they're getting pretty good. So if we validated our models through hindcasting, if they're able to accurately predict the present based on past data, then we can plug in our present data and try to forecast the future. The tricky thing here is that our models confirm for us that human activity plays a huge role in shaping our climate. And when we're hindcasting, we can just plug in the results of that human activity. We can just put into the model, we know how much CO2 is emitted each year because that's something that actually happened in the past and we have data on that, so we can plug that into our model and the model can use that to figure out what the resulting temperature is going to be. But when we're going into the future, that CO2 emissions from human activity that plays that big role in our climate is really hard to predict because people are hard to predict. People have the ability to make choices. People can look at the results of this model and say, I don't like that, we're going to do something different. We're going to try to avoid bringing that model's projections true. So we can't just spit out a single, here's what humans are going to do in the future in order to run our model based on that data. And so this leads to my hot take for the day, which is that social science is harder than natural science. And so I'm saying that on my authority as someone who has a background in both social and natural science. Social science is harder because people are complicated. We can predict the behavior of our non-human world a lot more easily than we can predict what people are going to do. So what that means is if we're trying to forecast, we're not going to do just a single forecast. We're going to construct a range of scenarios, a range of possible futures, things that we might do, and then we can run the model based on each of those scenarios. So we have sort of a if-then thing. If we put out this much emissions, then we'll get this temperature. If we put out this other amount of emissions, then we get this other temperature. So we get a range of possibilities. And so with these scenarios, you'll see this with running climate models that they show you results from multiple different scenarios. And there's two main ways that we can create these scenarios. So one of them is what we call a bottom-up scenario. So here we start by creating a range of plausible stories about what people might do in the future, right? We just think, okay, what's likely to happen with the growth of human population? What's likely to happen with our economy in the future, industrialization? What's likely to happen with new technologies that we might develop? What's likely to happen with possible policy options that we might adopt? And we construct several different stories about how the future might go, right? Some more optimistic, some more pessimistic, etc. Now, for each of these stories, we'll estimate how much greenhouse gases and other radiative forcings would occur under that scenario. So if we are predicting that we'll develop a certain kind of technology, then we will say, okay, well, that's likely to lead to this sort of change in the amount of greenhouse gases being emitted, et cetera, for all the other elements of that scenario. And so then once you have those future greenhouse gas emissions estimated, then you can use those to get your radiative forcings. You can calculate what the impacts on the Earth's energy balance are going to be from that. Then you feed those forcings into your model, and it gives you forecasts for the future climate based on each of those scenarios. So that's a bottom-up strategy where we start by telling a story about what we might do in the future and then infer the impacts on climate change of that. The other approach we can take is called top-down. So with a top-down approach, we start with a range of radiative forcings that we're interested in examining. So we say, all right, we want to see what things might look like at a radiative forcing of X watts per square meter at a certain point in the future. Then we work backwards from that and we say, okay, well, to get to this radiative forcing, what kinds of changes in greenhouse gas emissions and other things would we need to do to get to that point? And then once we have that that set of future changes in greenhouse gas emissions, then we can say, okay, and what would we have done to create that amount of greenhouse gas emissions? So we're basically working backwards as compared to what we do with a bottom-up scenario. So both of those are reasonable ways to create scenarios. Both of those have been widely used in climate models. So here's an example of some of the best known bottom-up scenarios created by the Intergovernmental Panel on Climate Change. And you'll see here, you don't have to know all the details of these scenarios, but just to give you an illustration of what goes into these scenarios. If you look at, say, the A1 family there, you can see the elements that they are speculating. This is a thing that might happen in the future. So global population peaks in the mid-century and declines thereafter. Future world of very rapid economic growth, rapid introduction of new and more efficient technologies, convergence among regions, and a reduction of regional differences in per capita income. Right? So those are all things that might happen to our world in the future over the next 100 years or so. And you'll see that one, they've even broken it down out into 3 sub-scenarios, depending on whether this rapid economic growth that they're talking about is primarily based on fossil fuel energy or other forms of energy, solar, wind, those kind of things, or some combination of that. And then you can pause if you want to read those other scenarios. They're just different stories about things that might happen in the future, right? Because if you take that first parameter of the A1 scenario, global population peaks in mid-century, declines thereafter, that's something that could happen. That's a very plausible future trajectory might be on, but that's not the only one, right? We could have an increasing population over the next century. That would lead to a different sort of scenario. You'll see that in the B2 family there, right? Continuously increasing global population. So we've got these different sort of stories that we can tell about our future, and from those we infer changes to greenhouse gas emissions over that time period, and from that we get our radiative forcings and we feed those into our models. Here are some top-down scenarios, and the top-down scenarios are the ones that the IPCC has kind of moved towards using more, so you'll see a lot more about these top-down scenarios. You'll see references to RCP, some number. When you see RCP, that stands for Representative Concentration Pathway. That's the name of a top-down scenario. The number is the watts per square meter of radiative forcing that we get to by the year 2100 under that scenario. So the RCP 8.5 scenario, we get 8.5 watts per meter squared of radiative forcing in addition to what we've got currently by year 2100. And then they've got here RCP 6.0, 4.5, 2.6. And for each of those, they have a pathway to get there. So how much greenhouse gases in CO2 equivalent, so that's CO2, and then all the other gases, greenhouse gases scaled to be equivalent in their global warming potential to carbon dioxide. What would we have to do over the course of this century to get to that radiative forcing by 2100? Okay, so again, key thing here, top-down scenarios, we started with a radiative forcing that we wanted to get to at the end, and then we worked backwards to figure out what might happen in our world that would get us there. Then again, we can feed these into our models to get some forecasts of our future. So here's some examples of some forecasts. So what you're seeing here, the graph is showing change over time from our kind of highest and lowest RCP scenarios. So the top one in the reddish color, RCP 8.5, the lowest one, RCP 2.6, right? Those are best and worst case scenarios. And then they've got the kind of average filled in there for those two other in-between scenarios on the far right side of the graph. And so with these, you'll see we've got your heavy line down the middle and then that kind of lighter range around it. That is, the heavy line is the average from all the model runs, and the colored in area is the range of all of the model runs. So same thing we were seeing on the diagram from when we were talking about hindcasting. You run the model a whole lot of times and then average them together. And so that gives you your average prediction and then your range of possible outcomes within that, that model. So our current GCMs predict our average temperature anomaly by the year 2100, so just under 80 years from now, of somewhere between 1 and 4 degrees Celsius, depending on which scenario you're looking at. And I put a note on there that the lower emission scenarios, which would give us the lower ends of that forecast temperature, probably already out of reach. Just in terms of what we're likely to actually do in terms of our political systems, our economic systems and stuff, what we're going to actually manage to carry out. Some of those lowest emission scenarios like the RCP 2.6, it's pretty unlikely that we'd actually pull that off. It's pretty unlikely that the world would actually do all the things that would be necessary to put us on that emissions trajectory that would lead to that 2.6 watts per square meter radiative forcing by 2100, and therefore keep our temperature anomaly to about 1 degree Celsius. You know, and again, this is social science, right? What are people likely to actually do? So this is a little more complex question than, you know, if we do this, what's the resulting impact on our climate? But we are probably looking at this point, probably at least 2 degrees Celsius by 2100, in my judgment of what future scenarios are the most plausible. We're looking at probably at least 2 degrees Celsius, but it could be higher, right? We could end up closer to the RCP 8.5 and get 4 degrees of warming. And then, so that's, you know, our biggest thing, or our first thing that we look at, is the total global temperature anomaly, but we can use these models to predict all kinds of other aspects of our climate system. So the second graph there shows sea level rise. And so you'll see there that sea level rise, again, depending on which scenario we're in, 0.4 to 0.8 meters by 2100. Again, those lowest levels are probably out of reach at this point. We're probably not going to get there, so we're going to be probably closer to the middle or higher part of that range for the sea level rise. And with both of these, you know, keep in mind we're running the model out to 2100 because, you know, as you can see, the amount of uncertainty in our model keeps increasing the farther out we go. So at a certain point, you know, it's not telling us much to keep running the model into the future and have just this enormous band of uncertainty about what's going to happen. But you'll see that the RCP 8.5 lines for both temperature and sea level rise are continuing to go up as they hit 2100. So we would expect that under those scenarios, they would continue increasing into the future beyond 2100 and even the sea level rise for RCP 2.6 going up as it hits 2100 because sea level rise responds more slowly to changes in temperature. So even if we were to, like in the RCP 2.6 scenario, halt our increased temperature at that 1 degree Celsius temperature anomaly, we would probably still see rising sea levels for a good bit of time after that. So then the last thing that I want to talk about is we've been running these models for quite a while. And we've had general circulation models operational for many decades, so it's worth looking back at some of the early model runs and seeing how they actually panned out. Because we run models at some point in time, and then time continues on. And so we start getting actual data that we can compare to the forecasts that our models made when we ran them at some point in the past. So the diagram here is looking at forecasts made in Hansen et al. 1988. It was a very important early paper on climate change that really put some of these projections of seriously increased temperature kind of on the map. And so what you've got here is the colored lines are showing you the scenarios as projected by Hansen et al. And then the black line is our actual observations. And so what you can see here is that some of their projections were pretty close to getting it. Some of the worst case scenario projections, we didn't get there. It didn't end up quite as bad as all that, but we've stayed pretty close to some of their more middle of the road average projections. And this is from 1988, so the state of climate modeling that we had way back then got pretty good results, and that's true for most of the climate models that we have. That when we look at past model runs, compare them to what has actually happened, taking into consideration that we now know things like what actual amounts of CO2 did we emit. We're not just reliant on scenarios that are kind of guessing about that. We find that the models tend to be pretty good. They've served us pretty well, though there is a subset of models that have tended to overestimate the temperature increases. And that's kind of a known thing, that there are certain models that have a tendency to overestimate, but most models are getting it pretty good. So we can have a good bit of confidence that the projections for our future that our models are giving us are reliable, that if we have the greenhouse gas emissions and the radiative forcings that the model was run based on, that the resulting temperature increases and so forth are going to match what the model has told us. So for your lab assignment this week, you're going to be examining the outputs from some simple climate model. So you're not going to be running a GCM because that would be way more computing power than your computer has, but you look at some simpler sorts of models, look at some outcomes, and use those models to forecast the impacts of some of our different policy choices that we make on the future of our Earth's climate.